Okay, so I have already written most of the parts. So let's start. So we'll show two proofs. So we'll show two deductions basically. The first deduction is we'll show that C5 contractibility is NP complete on bipartite graphs, and I will show this thing. And the next they will show that C4 is also NP complete. Right. So the goal is NP complete. Algorithm? No, there is no algorithm. Only reduction is there. Uh, okay. So this is our goal. Like we want to prove that it is NP complete. So like our goal will be this thing to we will reduce the problem of positive NAE-SAT to our problem, and we know that this problem is already NP complete, and our problem is I will define it in a minute. So this problem is already NP complete, and we'll reduce this problem to our problem in polynomial time. So let's define what is our problem. So the problem is of C5 contractibility. But first of all, what is C5 contractibility? So let's say we have a graph G. If this is our graph G, and what we want to do is we want to contract such sequence of edges such that the graph that we get after that is kind of like a C5. It is a C5. It is graph is C5. Right? So for example, let's say I have like partitioned the vertices of this graph G into five sets, right? And if you contract these five sets individually, right, so we'll get this graph. And as you can see, this is not C5 because there are edges like this. So this is not C5. But if you let's say the graph is like this and we partition it in this way, and then you contract all the individual components, then we'll get this graph, which is a C5. So we have multiple edges here, but that is allowed. Right? So this is C5. We are not adding, like it is there already because when you contract this edge, when you contract this edge, we'll have this multiple edge already. But I am not. I'm defining it this way. My convenience. And they didn't define. I was just showing an example. They didn't give me an example. So okay, so yeah, we can have it like this. No, it doesn't. It will not contribute. Ah. Mhm. Okay. Yeah. So the problem is only this. So given a graph G, we want to find a partition of these vertices such that once we contract all the individual components, do we get a C5 or not? So we have to find the existence of this witness set or not, witness structure. Right. So let's move on. So the property that we need for these sets are these things. That first of all, these five sets should be partition of V of G. Then each of the individual sets should be connected, because if they are not connected, then we can't contract into one vertices in that component. Right? And the other thing that we need is this thing that in this graph, it will have edge only. It will have only edges. It will not have any edges like this, or not it will have any edge like this, and it will have all such edges that are adjacent. So it is an if and only if condition. If there is an edge, so it should be adjacent, and if they are adjacent, there should be an edge. Okay. So this is our problem. Now the next thing is what is positive NAE-SAT. So the positive NAE-SAT says that given a CNF formula which contains only positive literals, so we don't have any negative literals, and we want to find a satisfying assignment of this formula such that in each clause at least one of the literal is set to true and at least one of the literal is set to false. So this is the definition, or you can say the problem positive NAE-SAT. And this problem is proven to be NP complete by this reduction. First we reduce SAT to NAE-SAT like without the positive constraint, and then we can reduce this problem to positive NAE-SAT, and this shows the NP completeness of positive NAE-SAT. We can also reduce directly from splitting SAT to this problem. So this is just a overview, like to give you a hint that it is actually an NP complete problem, right? So I'm just showing this reduction to show that it is actually an NP complete problem. Positive NAE-SAT is actually an NP complete problem. Okay. So let's move on. So let's move on to our main reduction that we want to do. Yeah, so this is our main goal. We want to reduce positive NAE-SAT to our problem C5 contractibility, and this should be on bipartite graphs, right? So the steps will be as follows. So NA2 SAT, NE2 SAT. Okay, so any two set is, I think it is two set only, so it is poly time. Uh, no, but it is a special variant. Right? We can solve two sets, so we can also solve the special variant. So okay, I think, let me think for a moment. Yeah, yeah, I think.
I think we solved this, any preset with a preset algorithm. And if we see that the assignment is satisfying the NA definition, then we are satisfying the assignment. If you, there might be multiple assignments, then can you solve this set? You do not find all possible assignments. You find one assignment, then it satisfies.
I think because it's just any set. I will think about it. So like the step with this thing, so we want to reduce positive any side to this problem. So we are given an instance of sad, just sad. So we will be given an instance of positive any set problem, and then we'll construct a graph from this phi, which we will call h. This graph will not be bipartite, and then we'll show that phi is an yes instance if and only if h is an yes instance, right? But this will not like achieve our goal because we want to prove for bipartite graphs. So then what we want to do is we'll construct a g from this h, and we'll show that h and g are equivalent. Basically, that h is yes instance if and only if g is yes instance, right? So we'll do this thing first, and then we'll do this thing later. Okay, so let's start. Okay, and this thing holds because of the transitivity of reduction. Yeah, so basically we are given an instance of phi, which is an instance of positive any set, and let's say the CNF formula has C1 till Cm m many clauses, and x1, x2, xn are the variables, right? And we know that all these variables appears in only positive form. So we can construct H as follows. So first, add a sequence of five vertices called as V alpha set, and these vertices are alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, and this will be in form of a C5 cycle. So this is the first thing that we do, and like we'll call this as a base cycle because if phi is a yes instance, we can like when we construct this H, the contraction that will happen, it will be like this cycle will be base, and all the contraction will be upon this thing. Now we have our variable gadget. So for each variable in the CNF formula, we add another cycle. We add another cycle C5, and the vertices are xi0 till xi4. So this is a variable gadget. Then we'll add the edges to this. So we'll add edges. So edges will be like this. Sorry. So we'll add two types of edges. The first edge will be of direct edges that connects xi alpha to xi p to alpha p. So this will be one edge, and the other set of edges are like the like cross edges. You can say kind of a cross edges because this goes like this. And I've denoted the same here. So the magenta edges are the direct edges, and the green edges are the crossing edges, right? And we'll do this for each. Huh? It contains quad cycle, and what was I trying to say? Yeah, so we'll do this for each variable. Like for each variable, we'll construct the cycle. And now we'll have clause gadget. So for clause gadget, we'll have only two vertices. So that vertex is called Cj and Bj. So for each vertex, for each clause, we'll add vertex Cj and vertex Bj, and we'll add four edges. So two edges will be from Cj to alpha 0, alpha 2 and alpha 0, and two edges will be from Bj to alpha 2 and alpha 4. So we add these edges in such a way so that when the contraction happens, this Cj will land in the same witness set as alpha 1, and this Bj will land in the same witness as alpha 3. And why is, I think the meet ended again. Meet ended again. So should I restart the meet? Meet ended. Okay, so it's fine. No, no. Yeah, so we are adding edges in such a way so that Cj lands in the same witnesses set as alpha 1 because Cj can't be in alpha 2 because then we'll have an edge between alpha 0 and alpha 2. Similarly for Bj. So we are ensuring that Cj lands in the same witnesses alpha 1 and Bj in alpha 3. Right? So now we have added all the gadgets independently for variables and clauses, but now we have to add the relation between variable and clauses. So what we do is for each, like let's say we have a clause we have a clause x1 or x2 and x3 or x2. Right? So here this is the first clause and this is the second clause. So what we can see for each variable that is there in, let's say for ith variable that is there in jth clause, let's say xi is there in cj, right? Then we add two edges from xi1, from xi1 j I to cj and xi2 to bj. So basically these edges. So for each edge, so for each variable that is there in that clause, we add an edge cj to xi1 and another edge from xi2 to bj. And
So if extra is part of any clause
huh,
CJ, it will just add first and second copy to the cross
huh, correct.
cross variable.
So first copy is added to cj and second copy is added to bj. And also I forgot to mention that here we're adding these two sets of edges because these two sets of edges like in a way denotes the assignment of the variable. So if the variable is set to true, then we can contract using this magenta edges, and if it is set to false, then we can contract using this green edges. Like we will be able to contract, else we won't be able to contract. Okay. So this completes our construction for H. So this is our final construction for H. So like this will do for all J's and for all I's. So now let's look at some observation. So the first observation is that let's say we have any graph, right? So not related to the reduction. Let's say we have any graph which is a C5, right? And these are the vertices. So V0, V1, V2, and V4 are the vertices. And we want to we partition these vertices into non-empty sets. Right? So the observation is that in any partition of these two vertices into two sets, two non-empty sets, there will be edges going across. And why is that true? Because if there are no edges going across, then the part is not connected, the graph is not connected, and we know that the graph is connected. Right? So this is true. We'll use this observation somewhere in the lemma. Right? Let's define these things. So we define we group the vertices together. The uh, first group is xi0, xi1. Sorry, not like this. So we create these sets xi0, xi2, xi3. So basically x0 denotes all the vertices, the zeroth copies of all the variables. X1 denotes all the one copy of all those variables, and so on. And YC denotes all these CJ copies, and YB denotes all these BJ copies. Okay? Now what we can see is this thing. First of all the x zeros, x1, x2, x3 are independent sets because we didn't add any edge between two variables. And similarly, YC and YB are also independent sets. Right? And the second observation is that V alpha is a dominating set. So first of all, what is dominating set?
What is
So
B alpha?
so V alpha are these vertices: alpha 0, alpha 1, alpha 2, alpha 3. So what is a dominating set? So a set is called a dominating set if for all the vertices. So for all the vertices that is there in the graph, either that vertex belongs to the dominating set or there is an edge that is from the dominating set to that vertex. So we can see the dominating set because all the x vertices are connected to alpha vertices, and all the C vertices are also connected to alpha vertices. So that's why it is a dominating set. Okay. Now also, yeah, so these partitions this set also is a partition of the graph. This all these sets and comprising with V alpha is also a partition of this graph. Okay. Now these are the important observations, but these are not very hard to see. First of all, if you look at the basically what this it says is that there is an edge from alpha 0 to zeroth copy of x and fourth copy of x, and also to cj all cj's. Why is that true? Because we construct the graph in that way. Because let's say C alpha 0, it has a edge from to CJ to all CJs. It has an edge to all xi zeros and all xi fours. So that's how you can see that
Can you link that picture here? Can you copy that picture?
I can actually. Uh, I'll have to go to that software then, and I will not have a pointer there. So it's fine. I think I have I have copy of the picture later on. Okay. And similarly, you can see that alpha 1 is adjacent to x1 and x0 because of the construction, because alpha 1 is adjacent to x1 and x0, right? And similarly, we can see all these things. So all these things follows from the construction only. Right? So like this is the main lemma that we want to prove. So this, if you want to prove this lemma, then the reduction, like the proving of equivalence of the relation reduction is very easy. So what is this lemma? So this lemma says that, in simple word, it says that if H is a C5, like if H is C5 contractible, then uh, all, like let's say, okay, let's say W0, W1, W2, these are the witness sets of that contractibility, right? So this lemma says that alpha, like each of these witness set contains exactly one alpha. So basically we can have alpha 1 here, alpha 0 here, alpha 2 here, alpha 3, and alpha 4 here. But we can't have two alphas in one W, or like basically, yeah, that thing only, that each witness set contains exactly one alphas, right? So this lemma we want to prove, and we'll prove this by contradiction. So yeah, first of all, let's say it is a C5 contractible. Then we can say that the, like the graph, that the contract after contraction, the graph will look like this, right? It will be like, since it is a witness structure, so it will look like this, and we'll have these properties, that none of the witness set is empty, and we'll have an edge between two witness sets if and only if they're adjacent, right? So we'll show that, we'll show it by contradiction, by like falsifying this statement. So suppose not, then we'll have cases. So first case is, let's say the first case is that V alpha, all of the V alphas is there in only single witness set, right? So in that case, let's say V alpha is subset of W0 without loss of linearity. So in that case, we can say that W square is a, sorry, W2 is 5, because let's say there is some vertex in W2, right? So if there is some vertex in W2, then that vertex will also have an edge to W0, because V alpha is a dominating set. Since all of the alphas are here, so that vertex will have an edge from 2 V alpha, some V alpha, right? So that's why we'll have an edge, and hence this is not a witness set. So this is a contradiction. So now let's look at case 2. So case 2 is V alpha intersects with exactly 2 of W. So we'll look at two cases. So like so let's say V alpha intersects with W0, W1, and V alpha intersects with W0, W2, and other cases are similar. Like by symmetry, we can say that all the cases are similar. So the first case is V alpha intersects with W0 and W1. So what we can say is, uh, let's say these are the sets, W0, W1, W2.
The argument.
Same argument. So basically, all the V alphas are here, right? So none of the V alphas, none of the vertices can be in W3. And now let's say if V alpha intersects with W0 and W2 only. So now we can use observation 1 here. Uh, yeah, so all of the V alphas are in here, right? And now what we can see is this W. Okay, so let's define X is equal to W0 intersection V alpha.
Then how you will argue
Huh? No, no, no. This is a different.
why not W3?
No, because W3 is adjacent to
Oh,
W2. So let's define these two sets. Right? So basically, all the vertices that are there in W0 of V alpha, and all the vertices that are there in W2 of V alpha. And we can say that this X and Y is a partition of V alpha, right? And since it is a partition, we know that there will be an edge between W0 and W2. Since it is a partition of X and, since it is a partition of V alpha, and we know that V alpha originally was a C5 cycle, so there will be an edge between W0 and W2 by observation 1. If
so
you,
the same thing.
so I'm saying that since V alpha was already a cycle, right? So previously was a cycle, and we are partitioning it into two sets, right?
There will be any step.
So there will be edge between W0 and W2, and that is a contradiction, because we can't have an edge here, right? And all the other cases are similar. So case 3, V alpha intersects with exactly 4 of W.
Why didn't you consider
That is a bit harder. That is a bit harder. So we'll do it at last. Okay. So yeah, so let's say the all the V alphas are there in V0, V1, V2, V3, and we can also assume that alpha 0 is in W0. Right. So again, let's look at the structure only. So I will use red color. So let's say these are the structures, W0, W1, W2, W3, and W4. Okay. And I know that alpha 0 is in here. Okay. So now you can say that since W4 doesn't contain any V alphas, and I know that alpha 0 is adjacent to alpha 4 and alpha 1, right? By the construction, alpha 4 and alpha 1 is adjacent to. So alpha 4 and alpha 1 has to be somewhere in here. It can't be in W2 and W3. So basically that's what I'm saying. The alpha 1 and alpha 4 is a subset of W0 union W1. Right? And since it is intersecting with exactly four of them, so one of the alpha 2 will be here and one of the alpha 3 will be here, or the other way around. Alpha 3 will be there, alpha 2 will be here. Right? But what we can say is, okay, so what we can say is this thing. Uh, okay.
Now you need alpha 3 and
Mm.
alpha 4 are
So what we can say is, let's say, okay, so we know that alpha 1 and alpha 2 is an edge. So alpha 2 can't be in W3. So because alpha 1 is here, so alpha 3 can't be in W3. Right? And this implies that alpha 3 has to be in W3.
W2.
W3 because W. Okay, so I was saying that one of alpha 2 is in W2 and one of alpha 3 is in W3. So either alpha 2 is in W2 and alpha 3 is in W3, or alpha 3 is in W2 or the other way around. But I'm saying that alpha 2 can't be in W3
Alpha 2 can't be W3.
because there is an edge between alpha 1 and
Why?
alpha. So alpha 3 has to be in W3 because it intersects exactly 4. Right? But we also know that alpha 4 and alpha 3 is an edge. So that is a contradiction because we have an edge from alpha 4 to alpha 3. Right? Okay, now case 4 is V alpha intersects exactly 3 of W. And like we have many cases, but we like only there are only two main cases, and I only go with this thing, and the other will follow from the same argument. So yeah, so let's say we have this witness structure again, and we have alpha 0 in W0. Right? So this is the first case that V alpha intersects with W0, W1, and W2. Other cases W0, W1, and W4. So these are the two cases that will prove. And let's say the other cases W0, W2, and W3. This is not possible because uh, and then we'll have partition of W2, W3, and W0, and we'll have an edge between these things. We'll have a partition of V alpha that are there in W2 and W3 and W0. So there will be an edge between W0 and W2. Okay? And the next case is when V alpha, yeah, so it intersects at V0, V2, and V4, and by the same argument.
Again, W0, W, then considered partition.
Hmm.
Yeah.
So the next case is it intersects with W0, W2, and W4. So W0, W2, and W4. So again, it is a partition of these two vertices and this one. Okay, so it is also same thing. And W0, W4, W3 is same as case A. Like if you see by symmetry, W0, W4, W3 is same as W0, W1, W2. Right? And W0, W1, W3, we can again see that there is a partition W0, W1, and W3. Okay? So basically, we have two main cases to prove, but I will only prove this first one because the second one is pretty similar from the first case. Right? Okay. So let's say the alpha intersects with W0, W1, W2. Right? And I know that alpha 0 is in W0. Right? So by the same argument, so let's draw that structure again. W0. Okay, and alpha 0 is here. So now our sets are this one W0, W1, and W2. And by the same argument, since alpha 1 and alpha 4 are adjacent to alpha 0, so we can't have, okay, so alpha 1 and alpha 4 can be only here. It can't be in W2 because then there will be cross edges. Right? So alpha 1 and alpha 4 is a subset of W0 union W1. Right? And this implies that at least one of the alpha 2 or alpha 3 should be in W2 because it intersects exactly two of them, exactly three of them. But note that okay, so we have alpha 0 here, and alpha 1 and alpha 4 will be somewhere around here in one of these two, right? And now I'm saying let's consider alpha 2, right? So I know that it's possible that, okay, let's look at the other case. So I'm saying that alpha 2 and alpha 3 out of these two, at least one of them will be in W2, right? Then the other one can be either in alpha 0, either in W0, W1, or W2. But I'm saying that alpha 2 can't be in W0 because then alpha 3 and alpha 2 are adjacent, right? And similarly, alpha 3 can't be in W0. So basically, we can say this thing that alpha 2 and alpha 3 are in these two sets, right? So, in these two sets, right? Fine.
Anyway, what if alpha 2 is in W2
One second. Alpha 2 is in W2.
and alpha 1
Correct?
Then what is the problem?
No problem. But alpha 3 will have to be here only. It has to be here.
So you think alpha 2 alpha 3 needs to be.
Uh, but I also know that one of them will be in W. Both of them can't be in W. So now let's look at the property. So since W is a witness structure, I know this thing that there is no edge between W0 and W3, and there is no edge between W0, W1 and W3, and same for here. Then from here, what we can say is since alpha 0 is in W0, right? It's by assumption alpha
So this E H
edge between W0 and W3. Right? So since alpha 0 is in W0, this set, so there can't be any edge that goes from alpha 0 to W3
why will you write it twice?
because we have three conditions. That's why. So since alpha 0 is in W0, so there can't be any edge that goes from alpha 0 to W3. Right? So basically, neighborhood of alpha 0 can't be intersecting with W3. Right? So this is 5. Similarly, alpha 1 is in by this thing is in W0 W1, so there can't be any edge going to W3. So we have this condition, and similarly for alpha 4 we have this condition. Right? Now, if you look at these observations that we made earlier, so if you look at this blue, only blue ones. So these blue ones are an alpha 0, an alpha 1, and an alpha 4. Right? And I know that W3 doesn't intersect with any of the threes, right? So if we see what are the sets that are left, x4, x0 is here, x1 is here, x2 is not there, x3, x4, yp, yc, all are covered, but only x2 is not there.
So
So I'm saying that look at these observations that we made earlier. So since we know that W3 doesn't intersect with this one, and this one, it can't intersect with these ones also. So what are the set that is left? X1, X0 is already here, X1 is there, X2 is not there, X3, X4, YC, YB, all are there, all are here. So W3 can only be a subset of X2. Right? And we can play this game again. So
what was this second copy?
second
Okay.
copies of X. Yeah. So we can again play this game. So W1 by definition this will be 5, and since we know that here, what is it? Yeah, from this condition that alpha 2 is in W1 union W2 and alpha 3 is also here. So we can say that neighborhood of alpha 2 with W4 is 5 and neighborhood of alpha 3 with W4 is 5. Same argument. And if you look at the pink, like the sorry, magenta ones here, we have all the so it says that it doesn't intersect in alpha 2 and alpha 3, and then it can't intersect all these sets. So it can only intersect with x0 x4 because x0 is not here and x4 is not here. Rest all are there. Now, since it is a witness set, I know that E of x, sorry, W3 and W4 should be non-empty, right? It should be non-empty. But I know that this two are empty. Like there is no edge between x2 and x0 x4 by construction. Like we constructed in such a way that there is no edge between zeroth copy of some element and second copy of some element. And this implies that there is no edge between W3 and W4 because W3 and W4 are subsets of these sets. So yeah, this is the contradiction that we are having. So again, the same one follows for this one. So I'm not going over this thing. Right? So now we can finally prove our equivalence that according to our construction, phi is S instance if and only if H is S instance. Right? So let's look at the forward direction. So let's say we are given a S instance of phi, and since it is a S instance, let's say pi is a satisfying assignment of this phi. So it's not phi, it's actually xi. Right? So phi is a satisfying assignment of xi. So now we can construct a witness set, and that will prove that it is C5 contractible. So this is the witness set that we have. So like we have a pattern. So first of all the alpha 0 goes to W0, alpha 1 goes to this thing. So this happens. And apart from looking at the definition, we can say that this thing that xip goes to WP if pi of x is set to true. So basically, if the variable is set to true, then it will go to the same witness set as its power. And if it's not set to true, then it will go to the next witness set. So here we can say that it will go to xi0 will go to W0 if it is set to true, and it will go to W1 if it is set to false. And if you see, this is like the same thing that is so earlier that if the variable is set to true, then we use the magenta edges. That is, it goes to the same witness set. And if it's set to false, then we use the green edges. So these are the sets that we created. So first of all, yeah, so we have to prove that the two three properties that
Where are false?
huh,
Where are false variables?
cross.
False, false.
Okay, yeah, it is here. YC is in W1 and YB are here. Yeah. So let's prove the properties that it is actually a witness set. So first of all, none of the witness sets are empty because each of them contains alpha. The connectivity property. Okay. So first of all, let's look at W0, W2, and W4. These are similars. So we know that each of alpha 0 is connected to Xi0, and each of alpha 0 is also connected to Xi4. So these are connected. Right? And similarly for W2 and W4. Right? Now for W1, this thing still holds that alpha 1 is connected to Xi1 and alpha 1 is connected to Xi0. We just need to show that these closed gadgets are also connected. These are not isolated from this set. Right?
So this is how we construct it. C copying the correct one.
Hmm? No, C is not connected to 1.
CJ was correct
C is connected to alpha 0 and alpha 2. So if you look at the diagram, it is connected to alpha 0 and alpha 2. Yeah, so basically we need to show that there is this edge. This edge is there. Okay? And this edge will be there because it is a satisfying assignment of NAE-SAT. So let's prove it formally. So basically we need to show that for W1 and W3, this is the situation that these three are connected, but YC might be isolated. So we just need to show that there is some X1. Okay, so basically we need to show that there is some X1 here. This X1 set is not empty. Right? Because if there is some X1, then then we'll have an edge, right? Then we'll have an edge between YC and X1. Okay, so I'm saying let's say there is a clause. Let's say there is the clause is jth clause, right? And the vertex was Cj. So basically, we need to show that Cj is connected to some xi1 by this construction, this dotted construction. Okay? And
that CJ is satisfied. So there will be someone.
so that's the argument.
So
So that's what I was said that for all j's, there exists a variable such that it is set to true. So this means that xi1 is in w1 because it is set to true, and this implies that since this variable is set to true, so cj xy1 is an edge, and this implies that yc is not isolated. And same argument for bj, that in that same clause there is some I prime that is set to false, and this implies that xi prime 2 is in w3, and this implies that this
this
is
is the point where you are looking
using
at
the
it.
NA set. So yeah, this is connected. Now the third property is that there should be an edge if and only if they are adjacent. So it is not hard to see. First of all, we can see that forward direction is correct. That there is an edge between alpha 0, alpha 1. These edges are already there. We just need to show that there are no cross edges, but that we can show by construction. I'm not going over that because that will be messy. So I'm not going over the backward proof.
But
Like it is just a case work that just see like there are no edges from W0, W2, no edges from W0,
whether we are
W3.
not using reverse direction.
So it is just a case work that there are no edges from here to here. Right? So forward direction is because there is an edge between alpha 0, alpha 1, alpha 1, alpha 2, alpha 2, alpha 3, and so on. Okay, so this is the forward direction. We have proven the forward direction. Now the backward direction, which is a bit tricky. So this will require certain claims. Okay, so
How we can
30 minutes more. 30 to 40 minutes.
30 40 minutes. Is it
I already said till 8:30. Timing is okay. So the backward direction says that so given a h which is a s instance, we need to show that we can construct a okay. So we can show that it is a satisfying assignment. The phi is a satisfying assignment. So let's say that W is the witness structure that we have for h that because it is yes instance, and we have this condition that it is a there is an h if and only if they are adjacent. Right? And we also have that this set shouldn't be empty, right? Because it is a safer structure. And by lemma 1, we already showed that every witness set has exactly one alpha. Okay? Now we'll show a stronger, like we'll show another thing that let's call Si all the copies of a certain variable, like all the copies of a variable Si. Then I will also show that Si intersect with all the W's. Basically, W contains is one copy of each. Like a W contains exactly one Xi is one copy. Okay? So suppose like let's say this is not true, then let's say some Si doesn't intersect with W0, or we can by the same argument. Let's say without loss of
the
generality.
same argument for that for C5?
Huh?
Isn't it the same argument for that for the C5?
No, I think this will be shorter basically. And basically this uses lemma one, so I think this can be a same argument also. Yeah, so suppose some SI doesn't intersect with W0, it can be WP also, but I'm taking W0. So then we can say that. Okay, so let's again construct the witness set here. This thing is here. W0, W1. Okay. So we know that all the alpha zeros. Okay, so I'm assuming that alpha zero is in W1, alpha one is in W1, because if it is not there, then we can rearrange W's. Right?
You do it. That's all.
So I'm assuming that since all alpha, like each witness set contains exactly one alpha, so I'm assuming that alpha zero is in W0, alpha one is in W1, because if it is not, then we can rearrange. So I'm assuming that all the alpha I belongs to Wi, because if it is not there, then we can rearrange W's, like we can rename W's, right? So this is true. So I'm supposing this thing that Si doesn't intersect with W0, right? But I know that Xi0 has an S from alpha 0 and Xi4 also have an S from alpha 4, right? So since it is not in W0, then these elements should be either both should be in W1 or both should be in W4. They can't be one in W1 and W4, because then there will be S between W1 and W4, because these two are also adjacent.
Zero and four are
Huh? Right. So they can either both of them are in W1 or both of them are in W4, and that's what I've written here, that either both of them W1 or both of them are W4. So suppose both of them are W1, right? Then I know that there is an edge between alpha 4 and Xi4 by construction. There is an edge between alpha 4 and Xi4. So alpha 4 is where? So alpha 4 is here, right? So alpha 4 is in W4, but I was assuming that Xi4 is in W1. So there is an edge between W1 and W4, and same for this thing.
they need to be no level four.
Huh?
They need to be level four.
So other cases this thing. So first case I'm proving this thing, that if they are both in W1, then we have a contradiction that this is an edge, and there if both of them are W4, then Xi0 and alpha 1 has an edge. Right? So this is a contradiction. So this proves that all the witness set contains exactly one SI, one copy of X. Right? So now the second copy is this thing. So this is actually a stronger claim that let's say again this is a witness structure. Sorry, this is also fine. Alpha 3, alpha 4, alpha 5. Then if I have a variable Xi0, then it can only belong to W0 or W1. It can't belong to anywhere else. And same for Xi1. It can only belong to W1 and W2. And why is that true? Uh, because okay, so this is the diagram that we have shown here. So alpha p is here, alpha p plus 1 is here, right? So let's take an example only. Let's say this is alpha 0 and this is alpha 1, right? And I want to show that Xi0 can only belong to one of them. It can't belong to anywhere else. So let's say it belongs to somewhere else. Then there will be S like this. That is a cross S. So I can show it like this also. So one, two, three. These are the four cases, right? So Xi0 is here. So if Xi0 is here, then we'll have this edge. If Xi0 is here, then we'll have this edge. If Xi0 is here, then we'll have this edge. So all the cases, there are cross edges. So Xi0 can only be in these two sets, right? Now another stronger notion is that uh, it says that if Xi0 is here, then Xi1 has to be here. It can't be anywhere else. And it is an if and only if condition, that if Xi1 is here, then Xi0 has to be here. And the other huh?
Same argument.
Kind of same argument.
Cross edges will be there.
Cross edges will be there, but yeah, correct. So, and the other argument is that if Xi0 is not there,
Yeah.
yeah. So other argument is that like Xi0 has only two options, either it can be here or here, right? So if it is here, then Xi1 is here. But if let's say if Xi0 is here, it can be here. So if it is here, then Xi1 has to be in the next set, basically alpha WP plus 2.
Then it cannot be in WP.
It cannot be in WP. We'll prove this. Basic, no, it can't be WP, right? Because it has only two choices, WP1 and WP plus 1 and WP plus 2. Right? So basically, I prove that it can't be in WP plus 1. So let's look at this one first, this proof. So the forward action says that it's fine. Right? So both the directions are fine. So after, like, we can use claim 1, claim 2, and claim 3 to construct a satisfying assignment, which is NAE assignment. Okay. So after all these claims, let's look at set W1. Look at set W1 and look at the copies of Xi1. If Xi1 is in W1, then set that variable to true. Just look at set W1. And if it is not in W1, then set it to false. Basically, we can do it for all any other also, but I'm just using W1. Okay. So then my claim is pi is actually a NAE satisfying assignment. So first of all, we'll note that this thing. Let's say again I have to draw this thing. Yeah, W0, W1. Okay. So first thing is CJ can only be in W1. It can't be anywhere else. CJ has to be in W1 because there is an edge between alpha 2 and alpha 0. So if it is anywhere else, so there will be a cross edges.
CJ can be okay.
And
CJ
can only be in W1 where alpha 1 is there. And similarly, BJ can only be in alpha 3 because there is an edge alpha 2 and alpha 4 there. Now, what I say? Yeah, so since like we know that W1 and W3 are witness sectors, so they are connected. So let's look at set W1. Okay. So W1 currently contains all CJs, right?
CJ is one, right?
W1 only. So I'm saying W1 contains all CJs, and it also contains alpha 1 by assumption because I said alpha 1 is in there. But I know that CJ is not directly connected to alpha 1. It is connected to alpha 2 and alpha 3. And I know that alpha 2 is in W2. So like CJ is like this. So CJ is like this and alpha 0, right? And there are no more edges apart from this. There are only edges that are dotted edges like these edges. And these edges connect to some xi1. Right? And for CJ to be connected to alpha 1, there has to be this edge. Otherwise, it is not connected. And if we have this edge, then some xi1 belongs to that w1. Right? So this means that this thing is true. That some I.
Same one can apply for PG.
So this proves that it is a satisfying assignment.
Oh yeah.
Now we have the last part that will so that it can be like we can derive a bipartite graph such that the C5 contractibility is still there. Okay. So this is a bit shorter thing. Okay. So what we'll do? So let's look at this. So let's look at we have this graph and now we'll this is H, right? This is H. This is H. So now we'll define a partition of this graph, and we'll show that this partition is not bipartite, but the edges which are there in which are there in L and which are there in R will subdivide those edges. Okay. So this is H, right? And we are doing a partition of this H of vertices. So L is as defined as this thing, and R is defined as this thing. Right? So first of all, it is clear to see that this is not a bipartite partition, or it is not a bipartition.
It is not. We
Huh?
know, like,
Uh,
so that it is a
yeah. So like to make it a bipartite, what we'll do, we'll like subdivide those edges that are there in alpha standard. Yeah. So the thing will look like this. So let's say if we have an edge that is there in UL, then we'll subdivide this and we'll call the vertex that is there here lambda UV, right? And basically we'll make this vertex here and we'll have UV here. So then this will graph will be bipartite. But now claim is this thing that G is bipartite graph. Oh, this is fine. This G is bipartite graph, but the claim is this thing that H is C5 contractible if and only if G is
but the
second.
new vertex will belong to wherever they belong.
The new vertex will be in the other part because if UV is in L, the new vertex has to be in R, and if UV is in like this case, right?
Right. So if you and me belong to the same
Set L.
same witness set,
No, I haven't said anything about witness set here.
yeah, but the group that you are going to know
So I think they can belong to same witness set, but we'll prove something else that I will prove that lambda UV can't be alone.
can't be of course.
So that will prove. And if it can't be,
You will put in any of the wherever you just put it with you or it doesn't matter.
I didn't get the question. What is the question?
So lambda UV cannot be alone, right? It will
Huh?
be either with you or
Either with you or we, or it can be also with both also.
it can also wherever you will be.
So basically, if okay, let's do it formally. So the first direction is pretty easy. That forward direction. If H is C5 contractible, then G is also C5 contractible because first we can contract G to H and then we can contract H to C5 because we got G from dividing edges. So then we can contract and get H and then we can contract H to get C5. So the forward direction is easy. The backward direction is obviously hard. Yeah. So let's say G is C5 contractible and the witness rate is again W0 to W4. Then I'm claiming that this thing will not happen. That this thing will not happen. That W0 is like some witness rate is not. It doesn't contain only lambda UV.
Wait, uh, G was your original graph or H was your
H was
original?
the original graph. So I'm claiming that W0 is like lambda UV will not be in a single witness set. It will not be alone, right? So for the contradiction, let's say it's alone. Right? Okay, so now that we have this situation that lambda UV, it is a single vertex, and this is a like this is a witness set, and since lambda UV has only degree two, one to U and one to V, so U has to be here and V has to be here in W
Why
one.
UV cannot be together?
Hmm?
Why UV cannot be together?
Okay, so
Okay, then lambda UV will not be connected to this.
then what? What is the problem if they are together?
So let's say you will be both one and double first, then how will you connect lambda UV with double two?
Correct. Yeah. So this is the situation, and now what we'll do is let's say this is our G, right? This is not G, but this is contracted G. Now let's say we look at the graph like G lambda U comma V. So we basically delete this vertex.
It's fine. UV anyway have H, so there is
Huh? What?
oh sorry. Go ahead.
So I am proving some contradiction here that let's say like the situation is like this. So now if we delete this lambda UV from G, so like this whole part is deleted, right? So now we can see that the shortest path from U to V is of length at least 3. And why is that true? Because
UV is an H, right?
huh?
UV is an H.
No, it is in H, not in G.
Right.
So in G there is no UVH.
Right.
So if you delete this lambda UV, then I'm saying that there will be shortest path between U and V is of length at least 3 because uh, one path is like this. But in this set, there might be multiple edges, right? The shortest path is at least 3. This is clear, right? So, but the contradiction is that it is not 3, it is actually 2. So this is the lemma. This is the claim that we want to prove that if some as UV was subdivided, and let's say lambda UV was that vertex that was introduced, then the shortest path between U and V is 2. And like this is very easy to see if you like. Let's consider all the edges that are subdivided, right? Then between lambda 0 and lambda 4, we have an vertex xi4, which has a path length 2. Like we can go from alpha 0 to xi4 and then to alpha 4. And similarly, for this edge that was subdivided, we can go from xi0 to alpha 0 and then come back to xi4. And similarly for all the vertices. Okay? So this proves that this is not true, that no witness set can contain only lambda UV. And now what we can do, we can simply remove all the lambdas from that witness set and that will be our witness set from H. And yeah, I have a bit of proof, but I think that's all.